Yum yum!
Hello, Łukasz Pazera from Pixel Fondue here. In this video we're going to talk about linear blend scanning. Linear blend scanning is probably the most common algorithm used to deform a mesh using skeletal structures. It's used in game engines such as Unreal and Unity, and its default deformation method in DCC applications such as Modo. The main advantage of linear blend scanning is the fact that it is not computationally intensive, while providing acceptable deformations in a good range of situations. It also supports all basic transforms, meaning translation, rotation, and scaling. That's not to say that linear blend scanning doesn't have any drawbacks. The main issue is a loss of volume with strong bends. So if I bend a geometry like that, you can already see that we're losing a volume around the bend area. And this is even more apparent when you twist a joint. Here we have something that is called a candy wrapper effect, and as you can see it's causing an extreme loss of volume, with the most extreme case being a volume collapse to a point. In this tutorial we will build a simple rig that replicates what linear blend scanning does for a single vertex. We will use a simple cylinder geometry and two joints that will act as transform effectors. This orange locator represents the point on the mesh that we're going to choose, and as you can see, as I apply rotation, this point stays at the exact same position as the real deformed point of the mesh. So let's take a look at what linear blend scanning does. We've got our simple model representation here, so that's the cylinder, and we've got two joints. The mesh is bound to these joints, and that means that each joint has a defined area of influence over the mesh. And the influence of each joint is defined by creating a weight map for each joint. On the weight map, we mark each vertex with a value from 0 to 1, defining how much influence a joint has over a given vertex. 0 means no influence and 1 means full influence. If a vertex is affected by multiple joints, all weight values for all affecting joints have to add up to 1. This is called normalized weighting. In our case, the influence of joint 1 is the magenta section here, and the influence of joint 2 is the blue section. As you can see, these are the areas that are affected by single joint only, and then in the middle we've got an area that is affected by multiple joints. And this is where the blending will be required to calculate the deformation effect. So let's see what happens when we bend joints like that. The first step in the linear blend scanning algorithm is to transform each vertex by each joint that has a non-zero influence on the vertex. These transformations are then stored. So if we talk about these areas here, which are affected only by joint 1 or joint 2 respectively, it's really easy. All the algorithm does is just transforms all those vertices by either joint 1 transformation or joint 2 transformation. So the effect for these parts of the mesh will simply be this. So here's section transformed by joint 1, and now we're gonna do, this is the section of the mesh transformed by joint 2. And that is the end of calculations for these vertices. To see what happens in areas that require blending, let's pick a point on the mesh that needs to be affected by more than one joint. So I'm going to pick this point right there. Like I said already, first we need to transform this vertex by each affecting joint and store these transformations. Okay, so let's see where this point will land when it's transformed by point 1. So it will probably be something like that, right? So that's, let's say, the version of the point as transformed by joint 1. And then let's do the same for the second. So for the second joint, so that's again is going to be something like this probably. And let's mark this version of the vertex here. Obviously, if there were more joints affecting this vertex, we would have to perform just as many transformations. All that needs to be done now is to perform a linear blending between all the transformed versions of the vertex using weight values from the weight maps defined for each joint. For simplicity, let's say that joint 1 has an influence of 0.5 on the vertex and the same influence has joint 2 as well. So now if I simply draw the line between those two, the deformed vertex will end up right in the middle, because it's just 0.5 and 0.5, so it's going to end up right there. If joint 1 had more influence, then this point would land somewhere to the left on the line, and if joint 2 had more influence, it would be the other way around. And that's it. I can extrapolate the remaining vertices from that. So let me just draw it roughly. So let's say that deformation would look something like this. It's obviously a very rough drawing. But in a nutshell, that's what the linear blend skinning algorithm does.
Yum, yum!